So hello and welcome. Welcome back, I hope, to another webinar from OpenEye Cadence Molecular Sciences. My name's Paul Hawkins, Principal Product Evangelist here at OECMS, and I will be your host for today's webinar. So from whenever and wherever you are, welcome. Today's presentation will be from Dr. Matt Geballe on novel hits from Beyond the Known, our tool ROCS X. Matt's going to give you, I think, a great presentation. He's very well fit for this particular topic. He's been at OpenEye close to 20 years now, joined directly from grad school at Emory University, where he was with Dennis Leota and Jim Snyder. In his long career at OpenEye, Matt's had a lot of different roles. He started off as an application scientist. He led the group that developed the tool he will be talking about today, ROCS X, and he's recently moved to an individual contributor role as a senior scientific development architect. So I'm looking forward to a magisterial presentation here. A couple of small housekeeping points. We do have the capability to take questions during Matt's presentation. So if you have any questions, please enter them in the chat on the right-hand side. We will try to get to all the questions in the course of the Q&A at the end. But if we don't, we will respond to your question by email subsequent to the webinar. So with that, I'll turn it over to you, Matt, for novel hits beyond the known.
All right. Thank you for that introduction, Paul. I'm going to be talking today about novel hits from beyond the known, searching trillions with ROCS X. So we cast our mind back about 8 years ago. That was when we first answered the question of could we search a billion molecules? And we delivered the capability to search a billion in Orion at that time, sort of beginning the era of what I think of as large-scale virtual screening in Orion at OpenEye. And it was 8 years ago. The show Silicon Valley was very popular at the time, so I went around giving talks, making lots of Silicon Valley references, and joking about getting Orion into the 3 comma club of being able to search a billion molecules. And this involved building a lot of the solutions that we now use regularly in Orion, things like running fast ROCs on the cloud, dynamically getting access to GPUs on the cloud and scaling those up and down, and using collections, our sort of distributed storage mechanism for running things in parallel at large scale on Orion. But 8 years later, this joke is out of date. The show is not on the air anymore, but the size that we want to search is also out of date. And so now we want to go from regularly searching billions of molecules to searching trillions of molecules. And so the question is now, can we get to the 4 comma club and search trillions of molecules? And you might think, well, a trillion is, it's only a trillion. It's not that much larger than a billion, but 3 orders of magnitude at this scale is pretty impressive. And I'll point out, if you search a billion molecules out of a trillion, you have about a trillion left to search. So we really have to think about how are we going to change our approach to drive the capability of searching to this new scale. And as we are often want to do at OpenEye, we want to look at history, look at including a quote. And so I went to the famous sci-fi author Isaac Asimov here and found this quote, which happily enough is from an anthology that he published called Only a Trillion. And he writes that even the purest and most high-minded scientists find it expedient sometime to assault the fortress of truth with the blunt weapon of trial and error. Sometimes it works beautifully. So that's just a little hint about the strategy that we're going to use to move from searching a billion to a trillion. So the real agenda for the presentation is to spend a little more time talking about searching larger and larger chemical spaces, why we might want to do that, why we think it's worthwhile, then talk a bit about the extreme scale search collaboration that we performed with Treeline that sort of provided the research foundation for this work. And then lastly, talk about the ROCS X product that we're building and how it enables searching unenumerated space in 3 dimensions. So out of that work 8 years ago, when I was making all those Silicon Valley jokes, came this publication that we wrote with AZ that they published in 2020. And it's confirmed the sort of things that we hoped would be true about searching larger and larger libraries, namely that it provides two important benefits. That if you search a larger and larger library, you find higher scoring molecules and you find more diverse hits among those higher scoring molecules. And those are both really strong motivations to search larger and larger libraries, because those are both important things in the early stages of hit identification. But searching larger and larger libraries also brings with it some cost challenges at each stage. The cost of preparing the databases go up, the cost of storing the databases goes up, and the cost of searching the databases goes up. But this isn't just an abstract challenge. The databases that we regularly want to search have been increasing in size over this period of time. And here I'm talking primarily about libraries of purchasable compounds from third-party vendors. These have grown rapidly in the last several years. Just to take one example that probably most are familiar with, the enamine real database. In 2021, that was 1.4 billion molecules. Since then, it's grown to 10 billion, to 17 billion, and now to over 24 billion molecules. So purchasable chemical space has grown and grown. The other thing that's really driven the value of searching these libraries is that chemical vendors have gotten very good at successfully delivering on the synthesis of these compounds. And so what we've observed is that as these libraries became more and more obtainable, the value of searching them went up as well. Because while it's useful to find a hit in a virtual screen, it's really useful if you can get that compound in the vial easily and get it into your assay. So as we think about the increase in purchasable chemical space, you might think, well, if that's all you need to do. But there are still really good reasons to want to search beyond purchasable chemical space. One of those is the things that we just talked about, the value of searching larger and larger libraries in terms of finding higher scores and higher diversity. But of course, you might want to search a different chemical space. You might want to customize the area that you're searching. You might want to search some different regions of chemical space than your competitors are searching. And so as we think about expanding search from beyond purchasable chemical space, but thinking about the value of building libraries full of obtainable compounds, that really raised the question to us, what is the next obtainable space that's beyond purchasable chemical space? And in our mind, this is what we would call easily synthetically accessible chemical space. This is a set of compounds that you can easily make from the building blocks that you have on hand or could easily purchase. And so this is sort of the philosophy of library design that we brought into the extreme scale search collaboration. This was a multi-year collaboration with Treeline that was centered around these two scientific goals. And these are simple but challenging. So first, to build a 3D representation of a library containing 1 trillion molecules. And then the second is to be able to search that library in 3D using a query either from a target molecule, so in this case, a sort of traditional ligand-based virtual screen, or using a query from the negative image of a binding site. I'm not going to talk much in detail about the negative image of a binding site aspect in this presentation, other than to say that all the search technologies that we build support both molecule queries and non-molecule queries. So going into this challenge, and as we started this work, we had a lot of things to build upon, a lot of the necessary ingredients. We have a lot of knowledge in doing conformer generation and ligand-based virtual screening at really large scale using tools like Omega ROCS and Fast ROCS that are best in class. We have knowledge of working with molecules in fragment form with Brood and structure-based knowledge from OE docking and doing that at very large scale as well. Not only do we have a lot of the knowledge from that, but we have those technologies available in toolkit form. So it's very easy for us to pick useful things out of those approaches and reuse them. And we also have a lot of cheminformatic knowledge wrapped up in our toolkit, specifically around reaction infrastructure, which we'll talk about in a few slides. And of course, we have the compute platform of Orion. We have this cloud platform where we have a lot of access to compute, both in terms of doing the calculations and in terms of storage as we need it. So we had a lot of the things that we needed. What we had to decide is how we're going to tackle this problem. And so if we think about these in stages, the first challenge really was, can we build a library of trillions of molecules, and how do we want to do it? And if we stay in this philosophy of focusing on building a library of accessible chemicals, that means, as I mentioned, molecules you can make in a reaction. And so we have to be able to understand reactions. We have to be able to recognize reagents from potential building blocks. We have to be able to assemble products. So we're really talking about building a traditional combinatorial library here. But if we're going to build a combinatorial library at this scale, we really want to keep it in unenumerated form. So keep it in the form of the building blocks that we can put together rather than the products. And the numbers here really make the point clear as to why you would want to do that. So if we take this simple example of combining 1 million star reagents and 100,000 triangle reagents, we see this would result in 100 billion products. And it's a lot more efficient to store 1.1 million reagents than to store 100 billion products. It's also a lot more efficient to search 1.1 million reagents than to search 100 billion products. But the search gets more complex if you want to search the reagents to be able to find the best products. But in terms of building the library, if we want to keep things in unenumerated form, then we wanted to leverage a lot of the reaction infrastructure that we'd already built around our generative design flows. And so this is the sort of multi-stage pipeline that we use for generating these unenumerated 3D libraries for the trillion scale. We start with building blocks, and these can be purchasable building blocks you have in-house. We pass them through our reaction infrastructure, which is really this set of interrelated cheminformatics definitions where we have moieties, which are synthetically relevant functional groups. We use those to build reagent classification based on the presence or absence of these moieties. And then we have a set of reaction definitions that define how you combine these into products and how you transform the reagents into those products. So we have a set of about 40 two-component reactions that we use, and we build a reaction reagent database by classifying all the reagents. But then we need to move this into synthon form, which means taking the reagents and removing leaving groups and getting it more into the chemical form that these would be in the product molecules. And so we transform all of our reagents into synthons and then generate conformers for them using our tool Omega to finally end up with our 3D synthon library. To give you an example of how this works and how we would build a trillion molecule library from this, in the course of the collaboration, we built several libraries. One of them ended up being about 3 trillion products. The input to that was about 7.5 million building blocks. This was actually the set of purchasable building blocks from 2 different vendors. Only about 60% of those we classified as a reagent, but many building blocks we classified as potentially being several different kinds of reagents. So when we transformed all of those into synthons, we ended up with about 20 million synthons. And when we generated 3D conformer ensembles of those, we enumerated unspecified stereocenters. And so we ended up with about 30 million 3D synthon conformer ensembles. Quite a number of synthons, but pretty small compared to the sizes of enumerated molecules that we've been searching. So we can prepare this library with about $40 of compute on Orion and it takes up about 126 gigabytes of storage. Just for a comparison, if we weren't going to go the unenumerated library route, but we were going to enumerate all 3 trillion products and then generate conformers for exhaustive search, you would need a large pile of money, because we would estimate that the preparation of this compute for that would cost over $10 million. The storage would cost about $400,000 a year because this would generate about 1.3 petabytes of data. And to do one search of this library would cost about $32,000 per search. So it's clearly much more efficient to build this library in its unenumerated form. But that leads us to the second challenge, right? How are we going to search this library and find the best products that we can out of this? And this is really getting us to the ROCS X approach, which is going to some of our favorite statistical methods, multi-arm Bayesian bandits and Thompson sampling. And so if you're not familiar with this multi-arm Bayesian bandits is a form of Bayesian search that's very powerful at deciding how to optimally sample a large decision space when you don't know the rewards in those decision space. And so that's why it's often explained by talking about playing slot machines. But this is a trial and error approach. So that ties back to the Asimov quote that I mentioned, where you sample the products here based on decisions, in our case, about choosing which synthons you're going to use. And you do that in a way to maximize reward. And we really like this method because it's an active learning method. So as you sample products and you learn about how those work, you improve and update your decision probabilities in a Bayesian way. And Bayesian bandits, along with Thompson sampling, sort of automatically balances the ideas of explore versus exploit. So you learn about the space at the beginning, and then you begin transitioning into more exploitation as you've done that. So this is a really appealing method. There's been some recent publications using this approach for virtual screening in our field, but an unsurprising turn for those of you who know OpenEye, we're going to build our system for doing this on the foundation of shape and color using the proven core of our ROCS technology. And so in our approach here, the arms, the decisions that you make are shapes, not individual synthons. And we build up this set of shape arms by fragmenting a set of high-scoring molecules against the query from an initial search. So this turns doing a search using ROCS X into a sort of multi-stage process where you start with a query and a library to search, just like normal. But here, at first, we need to build a hit list to initialize our model. And so you can do that by sampling some products out of your Synthon library and evaluating those against the query and using that hit list. But given that this is a query that you're interested in, you might have already searched that query against other libraries, against enumerated libraries. You might already know some high-scoring molecules. If you have an existing hit list, you can just pass that in to the model initialization. The next step is to build the Bayesian bandit model. So we fragment and discover the shape arms and search those against the Synthon library. This really leverages the power and efficiency of FastROCS. So we estimate we do hundreds of billions of shape comparisons just to initialize our Bayesian bandit model. But you can do that for a few dollars on Orion these days. So now that we have the Bayesian bandit model initialized, now we can search, which means we can sample products out of that model, and then we can evaluate them against our query. And so that is done by sampling a product and then using the familiar tools of Omega and ROCS to compare it to our query. So everything that ends up in the hit list, which is the highest scoring products that we sampled, are the result of a standard ROCS evaluation. So they look just like a ROCS, like your normal ROCS hit list. So at the conclusion of the ESS collaboration near the beginning of 25, we found some really encouraging results. When we compared our searches to the enumerated search of 1.7 billion shown here on the right, these are box plots of the scores of the molecules in the hit list. We see that as we search larger and larger spaces, we find higher and higher scores. So reproducing that encouraging trend that we saw from the AstraZeneca work, that searching larger libraries gives you higher scores. But we didn't go kind of as broad in our validation as we would like to. We just did this for a couple of queries. And we didn't do the full comparison between the largest library that we could search in the enumerated form, which was enamine real database, and using ROCS X. So for the rest of the presentation, I'm going to walk you through our more rigorous validation that we performed, which was using 15 different queries, choosing a shape-diverse set across 5 different targets. I'll show here. And this is derived from a data set that was curated for our 3D QSAR work that you may have heard about in recent webinars also. All of these queries were conformations from crystal structures, and I'm going to focus on walking you through the results for 3 different queries before talking about the overall statistics of our validation. So to give you a little more detail on the setup, we are now going to compare hit lists for searches of different databases. So in general, we're comparing a ROCS X search to a FastROCS Plus search of the enamine real database. But we're now searching different sets of molecules. And so there's some important questions that we want to understand out of this validation. So the first is, how do the scores in the hit list compare just in terms of their score distribution? Second is, because ROCS X is a sampling-based approach, we want to understand how the amount of sampling we do affects the hit list. And, are we finding better scores with more sampling? And then lastly is, how does ROCS X do as a probabilistic search at retrieving the best bangs that are available in the search space? And how can we actually know what those are when these libraries are becoming so large that we can't do an exhaustive comparison? So in the following slides, we're going to look at many results, and basics of the results are described here. So in the ROCS X search, we are searching a 3D synthon library that contains 1.3 trillion product molecules. It's a slightly filtered version of the 3 trillion molecule library I mentioned before. In general, we're going to do 1.3 million samples, which means we're going to pull 1.3 million product molecules out of that library. So that's only evaluating about 0.0001% of the 1.3 trillion molecule libraries. And then from that, we're going to take a hit list of the top 32,500 scoring molecules, which is just another sort of round fraction of the 1.3 trillion product space. It's an even smaller percentage, as you can see, although I'm not going to try to read out that number of zeros. So we're going to compare those hit lists using what we call a rank score plot. And so this plot shows the Tanimoto combo on the y-axis of the scores of the 32,500 molecule hit lists. On the x-axis is the rank of the molecules on the hit lists. So the top scoring molecule will be on the left, and will go all the way down to the bottom of the hit list on the right. So the exhaustive FastROCS search of the enamine real database, about 24 billion molecules, is going to be shown in teal. And the ROCS X search of the 1.3 trillion molecule synthon library is shown in red. But again, we're only doing 1.3 million samples out of that library. So these 2 curves here that I'm showing you are actually the curves from the search of our first query. This is a pretty simple, small query. And we didn't know that at the time, but this molecule is present in both libraries. And so we can see self-recovery of this molecule at the top of the hit list in both hit lists. And we've shown here the query in green, and then the top recovery from the ROCS X hit list in gray. And this looks like a normal ROCS result because it is. And so we see a very good overlay of the molecule there. But what we see is, from looking at this curve, is that the ROCS X hit list, as you go down the hit list, recovers higher scoring molecules than the exhaustive search of enamine real database, which is what you'd expect from searching a larger chemical space. But we're seeing it already, even just with our 1.3 million samples. So, we're finding higher Tanimoto combo scores, but we know from the very influential work from Steve Muchmore and others at Abbott that you can translate these Tanimoto combos into a probability of the molecule you find being at least as active as the query molecule. So you may have heard Paul Hawkins talk about this in several of his presentations about ROCS. This is what we call belief theory or the belief curve. And so if we can take this curve, and if we take just a sort of a round point on it, so let's say a Tanimoto combo of 1.7, which corresponds to a probability of activity of about 40% chance of being as active as the query, we can see, the increased scores from the ROCS X hit list means you found about 15,000 molecules that have at least 40% chance of being as active as the query versus only about 2,000 to 3,000 molecules from the exhaustive search of enamine real database. So searching a larger library and finding higher scoring molecules really can translate to improved chances of finding something as active as your query. So if we move from this small query to something a little bit more complex, a bit larger, we're seeing a separation of scores between the ROCS X hit list and the exhaustive search with FastROCS from the top of the hit list all the way down to the bottom. So we've got the top scoring molecule found in the ROCS X hit list shown here. We see its overlay here, very nice overlay. A lot of the molecule is similar, but a few interesting parts that are different. We can take the belief theory here and we can apply that to these two hit lists here. And if we don't do something as simple as taking a cutoff, but we take a more complex approach where we can treat each individual molecule in the hit list as a Bernoulli trial or say a coin flip with its corresponding probability of activity, we see if we look at the y-axis here, the difference in these scores is ripe in this region where the belief curve is really starting to increase rapidly. And so if we take each molecule here and treat it as a coin flip and do several thousand simulations of that, we can see that this increase in Tanimoto combos, we would estimate results in a 3 times increase in the prevalence of actives, at least as active as the query in these hit lists via this belief theory analysis. But, we've only sampled 1.3 million molecules out of the 1.3 trillion. What if we keep doing the ROCS X sampling a little bit more? Are we missing some great things in there? So if we instead do 6.5 million samples using ROCS X, so 5 times as many sampling, what we see is that there's not a lot of change at the top of the hit list. In terms of what are the best matches, we've pretty much found most of the best things that we can find. But as you go down the hit list, we see some filling in of the long tail, where we're starting to find a few more things that are higher scoring that make it onto the middle or the bottom of the hit list, to the point where at the end of the 6.5 million samples, now almost all of that 32,500 molecules in our hit list is higher scoring than the best thing that was found in the exhaustive search of the enamine real database. And we can apply our belief theory again and say that in this case, doing 5 times more work, we think gives us about a 70% increase in the prevalence of actives over the smaller amount of sample. But what if we have a really challenging query like this third query that's very large, very flexible? Here we're seeing pretty equivalent scores from ROCS X and from the exhaustive FastROCS search. The Tanimoto combos are lower if you look at the y-axis. The alignment that we get looks reasonable, but you'll notice that we're only finding a molecule that matches part of the molecule, not the entire query. So you might ask, well, maybe we're not doing enough sampling with ROCS X. Maybe we need to search more and we'll find something that's a much better match. And in this case, that doesn't seem to be the result. If we do 5 times as much sampling, the top of the hit list doesn't really move at all. You can see we find a few more things that make it onto the middle or the bottom of the hit list, but it doesn't really change things in a meaningful way. So in terms of, a needle in a haystack way of thinking, we aren't finding any more needles in this haystack by searching harder. But the question remains, how do we know there aren't needles in there? And one way we could test that, since we can't exhaustively search the whole thing, is we can sprinkle some needle parts into the haystack and change the haystack and then see if we can find those. And so that's effectively what we did here. We took 200 actives for this protein and we ran them through our preparation process. So we fragmented them up and then passed them through our reaction definitions and converted them into synthons. And then we sprinkled in those synthons into the synthon library. So augmenting a little bit the 1.3 trillion molecule product space. But now we know there's some active molecules in this set, and we want to see, can ROCS X find them? And so this is what the hit list looks like when we are searching a database with some of these active synthons included. So a dramatic change in the scores that we find. At the top of this hit list now is the self-recovery of our active molecule, which was formable from the synthons that we added. You can see the overlay shown here. And so what we see is that ROCS X is able to find and prioritize those synthons and use them to build higher scoring product molecules and pull those out of this very large product space, even in going back to the 1.3 million samples. So 2/3 of the discoverable actives that we added were in this hit list now after just 1.3 million samples, and 99% of the hits included at least one synthon from the fragmented actives. So we can at least convince ourselves that were there better things to find, we could find them very rapidly with this approach. So that's just some anecdotal look at the three of the 15 queries. But if we think about all of them and look at the statistical analysis across all 15, we can say some significant things here. So the first is to say that the scores of the ROCS X hit lists are statistically significantly higher than the scores from the exhaustive search. And that's true whether you look at the top of the hit list, the bottom, or the mean of those scores. And we can apply belief theory to say that those higher scores on average result in over 50% more actives in the hit lists. So there's a real value to being able to find these higher scoring molecules. There's not much in common between the hit lists, which makes sense given that we're searching a much, much larger space, only 0 to 2% molecules in common. And when we do sprinkle in these discoverable actives, ROCS X is able to recover over half of the actives across these 15 queries at 1.3 million samples. Although certainly we've seen some cases where we, given what we've seen, that we think upping the number of samples should increase the number of actives recovered. And then on the efficiency front, ROCS X and using the power of an unenumerated search and an unenumerated library is really efficient compared to the exhaustive search. So searching 1.3 trillion molecules with ROCS X is only 15 or 20% of the cost of doing the exhaustive search of 24 billion. And then not only is the search more efficient, but the fact that the library generation is also very efficient really enables you to do more flexible exploration of building different kinds of libraries and doing different kinds of searches if you're interested. So to conclude, we've made it to the 4 comma club. We can build libraries of trillions of molecules and we can search them. And not only we can search them, we search them in 3D, and we can demonstrate that we can produce higher scoring relevant molecules from these large spaces. So replicating the results that we saw with enumerated libraries in the publication with AZ, we can now show that in unenumerated space. We can find higher scores, and when we sprinkle in known active synthons, we have very encouraging retrieval of those with our probabilistic search. These are really efficient in terms of cost. So even though we're stepping up the size of chemical space that we're searching by 3 orders of magnitude, the cost of searching is actually going down. On the library building front, we can use this reaction-based approach to build these large libraries, and they're designed to contain easily accessible compounds in terms of actually being able to synthesize and get these compounds into vials. We haven't explored that ourselves, but in the course of our extreme scale search collaboration, Treeline was able to build these libraries and search them over the multiple years of this collaboration and apply them to real world projects. And in their words, they did this across several projects. They identified chemical matter and were able to get that made with a high synthetic success rate, and even to the point of getting multiple experimental structures with these compounds bound to targets. And over the course of the collaboration, they estimated that they sourced 150 compounds and had those made, and those were not in the vendor catalogs that they had been searching prior to this. So I'd like to acknowledge some of the people who worked on this, specifically Alex Lee, who built the Bayesian bandits search, and Bert Leland, who built the reaction-based Synthon library generation. We had a number of great collaborators at Treeline, Eric Manis, Brian Cole, and Andrew Fenley, we worked very closely with, and then a large set of people that we also worked with. Thanks to the science and cloud teams at OpenEye, we used a lot of their technology to do this. Particular thanks to Jinyi Chen, who curated the data set that we used, and thanks to Cadence leadership as well. And thank you all for your attention, and I'm happy to address any questions now.
So Matt, thank you for that. Magisterial as always. We've had a few questions come in over time, and I'll put a few of them to you now. First one, pretty simple. Do we support more than 2 component reactions in the current release?
Yes. So good question. The answer to that is not in the current release. So right now we only support 2 component coupling reactions, but we are very interested in expanding this, especially to 3 component reactions at least. That's probably something that we will be looking to add in a subsequent release after the 1.0 release. So not initially, but we hope to add that soon.
And just for everyone's information, when is the 1.0 release scheduled?
That should be in Q1 of 2026.
So soon. Very good.
Yeah.
This looks like a question from a chemist. To summarize, do we support deprotection reactions as part of the library enumeration process?
So our reaction definitions don't support protection or deprotection, but we are adding sort of a final deprotection step. So we should be able to draw products that both have protecting groups on or have them removed as if they were removed after the reaction. So we do intend to support deprotection in the 1.0 release.
Oh, okay, cool. Somebody was paying attention early on in the intro. You made reference to that work from AstraZeneca, where they were showing the impact on score distribution with increasing library size. And someone's noted that showed something of an asymptotic effect, as the increment you were getting in the Tanimoto combo scores was decreasing with each increment in the library size. And the question is, do we feel that we've reached sort of the effective limit with trillions, or are there advantages to going even larger?
That's a great question, and one we're quite interested in the answer to as well. We did notice that. And I think we'd like to see how that behaves as we expand searching larger and larger spaces. I have a hunch that some of that may be due to the way that those libraries were being built, which was more designed around having a central scaffold and then adding things onto that scaffold. So I think it's possible that as you got to larger and larger libraries, you had you were sort of seeing the exhaustion of, finding something interesting for all or most of the scaffolds that were placed in the center. But I think it's an open question. That's an interesting behavior to see, and I'm excited to see as we build libraries into the trillions or even larger, if we see that effect as well.
More science to be done.
Always.
Cool. Yes. And then how accurate are the predictions of the ROCS scores that were used in the ROCS X sampling?
Okay. So that's a common question. We're not actually building a model or predicting the ROCS scores at all in the Bayesian bandit model that we use. So all of the evaluation that we do and all of the kind of reward that we use to adjust the probabilities of drawing the different arms in our bandit model comes from a real ROCS evaluation of a product molecule against the query. So once we draw a molecule from our space, it goes through the normal steps of we have a SMILES, we run that through Omega, generate conformers, and then we compare those conformers against our query. So there's no kind of building a model to predict the scores, and everything you get out is the result of a real traditional ROCS evaluation.
So you basically get exactly the same result if you were to search the same set of molecules that you build from the syntons brute force versus doing it at the synton level. You get
Exactly. Once we've decided to evaluate that product molecule, it's exactly the same result as if that molecule was in an enumerated library that we had prepared, and then we're evaluating with a traditional ROCS screen.
Reassuring. Well, there are a few more questions that have come in, but we've actually run out of time. So Matt, as always, thank you very much for the presentation. I found it very educational. So for all of our watchers, viewers, thank you very much for your attendance. If you asked a question and we didn't get to answer it in the time, we will be responding by email over the next few days. So with that, I'll bring the webinar to a close. Thank you again for attending, and we look forward to seeing you at the next webinar from OpenEye Cadence Molecular Sciences. Until then, goodbye.